This is Water and Wastewater Treatment Engineering, Module 2, Water Treatment Engineering. This is part 3 of the lecture on water treatment engineering. We're going to talk about settling theory and sedimentation. Our objectives are to describe the different types of settling that occurs in sedimentation basins, apply discrete particle settling theory to calculate the terminal settling velocity, calculate overflow rates for rectangular and circular basins, and understand the design criteria and apply them to size a sedimentation basin. In part 4 of this lecture, we will be learning about filtration using media filters. So again, this is our typical surface water treatment plant. We've got coagulation, rapid mixing, and flocculation occurring in the first step, followed by sedimentation and or filtration. So today we're talking about the settling tank step, the design of this portion of the treatment plant. After flocculation, we've now got larger flocks of dissolved constituents that have coagulated into these larger settlable or filterable pieces that are then going to be removed in the settling tank. So there's 4 different types of settling. They depend mostly on the shape of the particles and on their concentrations. So if we see this graphic here on the right, on the y-axis we have the particle concentrations, so we have lower particle concentrations here at the bottom and higher particle concentrations up here at the top. And on the x-axis here we've got the shape of the particles. So if it's more of like a discrete shape, individual discrete particles, or particles that are coagulated into flocks, so flocculent shape on the right hand side of the axis. And you can see the graph is roughly divided into 4 quadrants. We've got type 1 settling, which occurs at particles that are mostly discrete and they're present in low concentrations. This is what we call discrete particle settling. The particles in this scenario, the particles would be settling without influencing other particles. If we have discrete particles but at higher concentrations, we might get type 3 or even type 4 type settling. And so type 3 is hindered or zone settling, where you have a large number of particles that form a blanket which can overtake other particles, kind of dragging them down with it. Type 4 settling, compression settling, happens when you get water being displaced from the pores as particles settle and compress, and that displacement causes the particles to become more compact. So that happens when you have very high concentrations of particles. And then the other type of settling is type 2, which happens when you have flocks, and this would be the case in water treatment processes. We have flocculent particles following differential flow paths and forming these larger flocks that'll settle at a different speed than the individual particles themselves. So again, to review, type 1, discrete particle settling, is where the particles don't interfere with each other during the settling process because there's a low enough concentration and they're not flocculating. This is the type of settling that we see in grit chambers, and also for water treatment plants, this is what we would experience in a pre-sedimentation basin, where we're really focused on the removal of larger, heavier items like sand prior to coagulation, flocculation. Type 2 settling, again, is flocculent settling. This is where either by velocity gradient in the sedimentation basin or differential settling, as time progresses, these particles and the flocks that they form are going to settle faster. This is what you find in most conventional sedimentation basins, specifically when using iron and alum coagulation processes. Type 3 zone settling is when you have blankets of particles that are formed, and these blankets create these sort of tarps that will drag down particles with it. This is found in thickeners, so like sludge disposal processes, and also at the bottom of some sedimentation basins, specifically if we're using, for example, lime softening processes in the sedimentation basin. Type 4 settling is compression settling. In this mechanism, the particles may not settle as much, but the water may flow or drain out of that thickened kind of blanket of particles. This is what we really see with dewatering operations for solids handling. So type 1 discrete particle settling, we could, for this mechanism here, we can picture the particle that's settling as being acted on by the force of gravity, right, which is pulling it down, and two forces which are pulling it up, which is the buoyant force and a drag force. So we can denote these by F sub G, F sub B, and F sub D. Therefore, according to the laws of physics, we know that the sum of these forces acting on the particle must be equal to 0. So we can convert that equation into the following form based on our knowledge of the density of the particle, the volume that it occupies, and the acceleration due to gravity constant. We can also take into account the drag coefficient as well as the projected area of the particles in the direction of flow. So you can see that this equation is equivalent to the more detailed form here shown on the right. For a spherical particle, the following equations can be used to estimate the particle's volume, the particle's surface area, and the mass of the particle. And we can also define Reynolds number using the same parameterization with regards to the particle's shape, mass, density, etc., the settling velocity, and if we take into account the viscosity as well of the water source, we can estimate the Reynolds number for a sedimentation basin. The drag coefficient is then a function of that Reynolds number, and for spherical particles, which we can assume that most particles in question are approximately spherical, the drag coefficient can be given by the following expression, where it's equal to 24 over the Reynolds number. If the Reynolds number is less than or equal to 1, this would be for laminar flow conditions, and it's equal to this expression for situations where the Reynolds number is larger than 1, but less than 10,000. That would be kind of the transition from laminar into turbulent flow conditions. So according to Stokes' law, spherical particles with laminar flow conditions, we can calculate the settling velocity using the following equation, which relates the density of the particle, the density of fluid, with the particle's diameter, and the viscosity of the water. Newton's law would apply for spherical particles where we're in that transition phase, where the Reynolds number is greater than 1. So here we can calculate the settling velocity under these conditions using Newton's law and the following equation here, which incorporates the drag coefficient. So in order to determine the settling velocity, this is the procedure that we would use. Step 1 is to use Stokes' law to obtain an initial guess for the settling velocity. Step 2, we're going to use that settling velocity that we initially guessed in step 1 to calculate the Reynolds number. Then step 3, we're going to look and see, is that Reynolds number greater than 1? If so, we'll go to step 4. If not, then Stokes' law is valid, and the settling velocity calculated in step 1 would be the final answer. However, if our Reynolds number is greater than 1, we need to calculate the drag coefficient using that Reynolds value, and then calculate the settling velocity using Newton's law, which relies on the estimate of the drag coefficient. So you can see it, at this point it becomes an iterative process, where then we would recalculate the drag coefficient using the new settling velocity and repeat steps 5 and 6 until we get convergence in the estimate of the settling velocity. So convergence being defined as, we continue to repeat these steps 5 and 6 until the settling velocity that we're calculating using Newton's law is not really changing much from one iteration to the next. So let's do an example problem. Let's calculate the terminal settling velocity of a sand particle in a water source at 10 degrees Celsius, having a particle diameter of 100 and 200 microns and a density of 2,650 kilograms per cubic meter. And here are some values for viscosity at 10 degrees Celsius. All right, so for this one, we're going to follow the procedure outlined in the previous slide. Let's start by doing the example of a particle with a diameter of 100 microns. and then we will do the same example with a particle of 200 microns. So for the first one, let's start by using Stokes' law. To obtain the initial guess of the settling velocity. So again, that is settling velocity is equal to G times rho sub P minus rho multiplied by the particle diameter squared. That's divided by 18 mu. Alright, so that's equal to 9.81 meters per second squared. And the difference in densities is 2,650 minus 1,000. The units there are kilograms per cubic meter. Then we've got the particle diameter, which is 10 to the negative fourth meters, and that's squared. In the denominator, we've got 18 multiplied by viscosity, which is 1.307 times 10 to the negative 3, and the units there are kilograms per second meters. Alright, so that should be equal to 6.88 times 10 to the negative 3 meters per second. So that would be the settling velocity of this particle with a diameter of 100 microns. Step 2 is to calculate the Reynolds number using that settling velocity. So the equation for Reynolds number again is Reynolds number is equal to particle diameter times the settling velocity divided by V, and this is equal to 10 to the negative fourth meters times 6.88 times 10 to the negative third meters per second divided by 1.306 times 10 to the negative sixth meters squared per second. So it's unitless, and it is equal to 0.53. Alright, so this first check, Reynolds number is less than 1, therefore we are done. And we can say that the settling velocity is going to be equal to 6.88 times 10 to the negative third meters per second. Alright. If we were to do the same problem, but this time focusing on a particle with a larger diameter of 200 microns, then we would have to change here this parameter right here in step 1. So we would still start with the first step using Stokes' law to get an estimate for velocity. This would be 2 times 10 to the negative fourth instead of 10 to the negative fourth. Everything else remains the same. This would then equal 2.75 times 10 to the negative 2 meters per second. Alright, so we have a new estimate at velocity. Then we're going to use that velocity to calculate the Reynolds number. So this value here and this value here is going to change. So we're going to have 2 times 10 to the negative 3 and 2.75 times 10 to the negative 2. And that's going to give us a Reynolds number of 4.21. Alright, so in the second case, the Reynolds number is greater than 1. Therefore, we need to go on to step 4. So step 4, alright, so we need to proceed to step 4. So in step 4, now we're going to take that Reynolds number and we're going to use it to estimate the drag coefficient. Alright, so that equation is C sub D, the drag coefficient, is equal to 24 divided by the Reynolds number plus 3 over square root of the Reynolds number plus 0.34, which will give us a value of 7.50. Now we're going to use that drag coefficient to calculate the settling velocity using Newton's law. So settling velocity according to Newton's law is equal to the square root of 4g times the difference in density times the diameter of the particle divided by 3 C sub D times rho. Alright, so this will be equal to 4 times 9.81 meters per second squared times 2650 minus 1000 kilograms per cubic meter times 2 times 10 to the negative 4th meters. This was a mistake down here. This should have said 2 times 10 to the negative 4th meters, not 10 to the negative 3rd. Alright, so then this whole thing is divided by 3 multiplied by 7.5 multiplied by 1000 kilograms per cubic meter. And that gives us a value of 0.024 meters per second. Alright, so you can see that's slightly different than our initial guess of 2.75 times 10 to the negative 2, or 0.0275. So next we're going to move on to step 6, which is to recalculate the drag coefficient. Using the new settling velocity. Alright, so C sub D again is equal to 24 divided by our new Reynolds number, which, if we were to calculate it, should come out to 3.67. So we're going to recalculate the Reynolds number because we need to use that in the drag coefficient equation. But again, the Reynolds number is calculated based on the settling velocity. Alright, so I skipped that step here, but you should get a value of 3.67 using this new estimate for settling velocity. So we're going to use that to calculate the drag coefficient, so 24 divided by 3.67 plus 3 divided by square root of 3.67 plus 0.34. And that gives us 8.44. Slightly higher than we had before. So then we're going to repeat back into this step. And instead of using 7.5, we're going to substitute for 8.44 instead. Alright, we keep repeating this process until we get a convergent answer. So for this problem, the best way to set it up would be to do it in Excel instead of doing it by hand. So we would set up the series of equations in a table. For example, we might have settling velocity in one column, Reynolds number in another column, and the drag coefficient in the third column, and then maybe we have the iteration number. So on the first iteration, we get a value of approximately 0.028. As you saw using Stokes' law, that produced a Reynolds number of 4.21 and a drag coefficient of 7.50. The second iteration gave us an estimate for settling velocity of 0.024, a Reynolds number of 3.67, and a drag coefficient of 8.44. The third iteration, 0.023, 3.46, and 8.88. So on and so forth. By the time we get to the eighth iteration, you'd see that the settling velocity is remaining constant at 0.022. The Reynolds number is staying constant at about 3.31, and the drag coefficient is staying constant at about 9.23. So at that point, when we see these numbers staying the same, we can stop, and this would be our final answer for settling velocity. All right, so there's two different types of unit processes where we might use sedimentation. The first is in some water systems, like where there's a higher concentration of solids, such as if we're using river water, we might use a pre-sedimentation step before we get into coagulation flocculation. That pre-sedimentation is used to remove easily settleable particles like sand, grit, silt, which we would often find present in these river water supplies. This will avoid silting up inlet piping in the treatment plant, and overall provide better performance of the system over the long term without the need for so much maintenance. Pre-sedimentation basins would be located upstream of the raw water pumping facilities, so we would site them as close as possible to the intake structure. So the other place in the treatment plant where we would use this type of reactor is after flocculation, as we discussed, having a settling tank, sedimentation used to remove particulate matter, chemical flocks, and precipitates from suspension via gravity settling. There's a few different types of configurations we can use to design sedimentation tanks. The two most common configurations are to have circular sedimentation tanks, as you can see here, where you have the water coming into the sedimentation basin, comes in through the middle, through the center. It is discharged through openings in this inlet pipe where it'll, for example, in this case, you can see the baffle here. It'll travel around the baffle and then move outwards radially until it goes up and over a weir at the edge and exits the reactor through the outlet. The settled solids in the sludge, which is produced in this reactor, would then be removed from the bottom of that system. So here you can see a plan view where you have the effluent channel. The water's coming in through the middle, it's traveling radially outwards and then over a weir into the effluent channel where it then exits the reactor, as you can see here. The other type of configuration that's very common is a rectangular sedimentation tank. So here we would have an inlet pipe. That inlet water would be dispersed using some kind of baffle or dispersion structure where you'd have some openings for the water to pass through and try to spread it out evenly throughout the reactor. We would then have the water moving horizontally from left to right. And in this plan view, you can see here at the effluent, we'd have some effluent channels where the water would come over the tops of weirs into these channels and then drain out to the outlet, as you can see here. So you have the heavier solids are settling down to the bottom and they're removed from this point in the reactor as sludge, and the water is flowing over the weirs into the outlet channel to move on to the next process in the treatment system. So this is what discrete particle settling would look like in a rectangular basin. We've got two components of the particle velocity. The two components are the settling velocity, which is constant for a discrete particle, and the second part is the fluid velocity, which is constant for a rectangular sedimentation basin. So let's suppose we have a particle that comes into the sedimentation basin here up here on the top. So if this were a cross-section view of the rectangular sedimentation basin, and we have a particle that comes in on the top at height h sub 0, that particle would need to travel vertically all the way from the top down to the bottom in the settling zone. So we can have, depending on the particle, its properties and its relative settling velocity compared to the flow velocity. You can see here if it was particle 1, which would be a lighter particle, doesn't settle as fast, you can see it has a lower settling velocity. This particle might start to settle, but might never make it down to the bottom before reaching the end of the reactor. Particle 2, on the other hand, is a particle that might start at the top again, just like particle 1, but compared to particle 1, this one has a higher settling velocity, so you can see that it will travel all the way down to the bottom of the reactor just in time before making it to the effluent point. Particle 3 here, you can see, has a similar trajectory as particle 1. However, instead of starting up at the top here, it's going to start, let's suppose it enters the reactor halfway. So it has a slower settling velocity, but it only has half the distance to go. So this particle, just like particle 2, would make it all the way down to the bottom before reaching the end of the reactor. So in this case, particles 2 and 3 would be settled out. Particle 1 might not be settled out from the water. Using that fundamental about the two fundamental assumptions here, that the settling velocity is constant for a discrete particle and that the fluid velocity is constant for a rectangular sedimentation basin. And we can calculate the fluid velocity, remember, based on the flow rate and the cross-sectional area of this reactor. Based on those fundamental pieces, we have a particle that enters the inlet zone at the top of the basin and settles into the sludge zone just before the outlet, which in our example before, that's particle 2 in this case. We would call that particle 2 the particle that has what we would call the critical settling velocity, V sub c. So this means this is the minimum velocity that a particle can experience in order to completely be settled out to the bottom of the reactor, even if it enters into the reactor at the highest possible height. All right, so any particle, based on, after defining that critical velocity, we can say that any particle in the inlet zone with a settling velocity that is greater than or equal to that critical velocity will be removed regardless of its vertical starting position. So if it starts down lower, of course it'll still be removed, but even if it starts to appear way at the top, it would still be completely removed by the end of the reactor. However, particles with a settling velocity that is less than V sub c may also be removed, but that would depend on their position at the inlet. So that would be the case of particle 3, where you can see particles 3 and 1 have identical settling velocities. However, particle 3 is removed, particle 1 is not, and that's just because particle 3 comes in halfway up the reactor, whereas particle 1 comes in at the very top. All right, so the critical particle settling velocity is calculated as follows, where we have the height, the maximum height at which that particle can come in, divided by the retention time, which is also equal to Q over A. And we can see how that works out, because if we substitute retention time for volume divided by flow rate, the flow rate goes in at the top here, and the volume comes in at the denominator, and the volume is equal to the height multiplied by the area. So in this area here would be the surface area, looking down on it, on the reactor with a bird's eye view. So these H zeros cancel out, and we're left with Q divided by A. Now that critical settling velocity is also defined as what we call the overflow rate. So this overflow rate is really used to design sedimentation reactors that are rectangular in particular. So overflow rate being equal to Q divided by A. So there are two components, again, of particle velocity. It's settling velocity, which is pulling the particle down. And as we said in the previous example, that's constant for a discrete particle. And then we have the fluid velocity, which in a rectangular basin is considered to be constant because we have a constant cross-sectional area throughout the entire basin. And if our flow rate remains constant, then that velocity is going to be constant. However, in the second type of sedimentation basin, the circular basin, even if the flow rate remains constant, the fluid velocity is going to change as it moves outward toward the edge of the reactor. And the way that that fluid velocity changes can be defined according to the equation shown here on the right. So we have that fluid velocity in this case would be equal to the flow rate divided by 2 pi r minus r sub I multiplied by h sub 0. So again, h sub 0 being that height at which it enters. If it enters right in at the top of that inlet zone, then we have the velocity starting out slower and then becoming greater as the particle gets closer and closer to the outlet. So you can see here, again, we have particle 1 and particle 2, which you can imagine if particle 1 comes in at the maximum height and it has a settling velocity such that it will settle right before it gets to the outlet zone. Particle 2 has a similar trajectory in terms of the settling velocity. However, it enters at height h sub s instead of h sub 0 and settles out even before reaching the far before reaching the outlet zone. All right, the reason that this velocity changes in a circular reactor is because we start off, we have a constant flow rate, but this inner inlet zone, this inner circle here, if you imagine that as being a cylinder that we could unfold and make into a rectangle shape, the area, the cross-sectional area that the water is passing through is smaller here at the inlet than it is here at the outlet. So if you have the same flow rate going through a smaller area, the velocity is going to be greater, moving horizontally. So the settling velocity, again, is constant, but the fluid velocity moving horizontally from the inlet zone to the outlet zone is going to start off very high, very fast, and then it's going to get progressively slower as the particle moves closer to the outlet zone. And that's because the area is increasing as the particle moves away from the inlet radially. And so if we could, again, compare the cross-sectional area of this inlet zone here at the very inner portion of this reactor compared with the surface or the cross-sectional area of this outlet zone, the baffle here at the outlet zone, the larger circle produces the larger cross-sectional area. So therefore, at closer to the outlet, you're going to have a slower fluid velocity. So again, we can define a critical particle settling velocity. However, the equation is going to be slightly different, so it still would be equal to h naught h sub 0 divided by the retention time. However, the retention time here still being equal to volume divided by flow rate, but that volume factor is going to be calculated as h sub 0 times pi times the difference in the square value of the radius, where you have the inner radius here, r sub I, and the outer radius here, r sub 0. So again, that would be equal to Q over A, where Q is the flow rate and A is that surface area, right, where the height here, h sub 0, is canceling out, so you're left with the surface area, as you would see in a plan view, and that is equal to the overflow rate. So criteria that we use for sizing sedimentation basins, it's based on the detention time, as we mentioned. So you have the longer detention time of a basin, and we can express that in hours. The longer the detention time, the better settling performance we're going to get, because we're giving more time for those slower settling particles to settle down to the bottom. It's also based on the surface loading rate, which is what we call the overflow rate, right? And that's overflow rate equal to Q divided by A. It's also proportional. The criteria that we use for sizing sedimentation basins is also based on the weir loading rate. So with the weirs, as I mentioned in the previous slide, are set up at if it's a circular basin, they're set up at the outlet, at the outermost part of that basin. If it's a rectangular basin, then they appear at the end of the basin. However, they typically protrude up, extending up a certain distance into the sedimentation basin. So if in this photo here on the right, if you imagine the water coming in somewhere around here and progressively moving towards the outlet, which is on this end, you can see that the weir structures are protruding into the sedimentation basin and allowing the water to overflow along this entire length. So the purpose here is to extend that length as much as necessary in order to maintain a flow velocity over the weir that's not too fast, because again, we want to keep that flow velocity low so that we don't get the resuspension of particles or material that can be settled. So the weir loading rate, which is calculated as Q, the flow rate, divided by the total length of this weir at the effluent, that's another criteria used for sizing sedimentation basins. The fourth criteria here is the horizontal velocity, and this is relevant for rectangular tanks only. So the horizontal velocity being equal to Q, the flow rate, divided by the cross-sectional area of the basin. And some guidelines for sedimentation basin design, and these come from the 10 state standards, that we typically want to maintain a minimum of at least 2 parallel units, although in some plants you might find more than 2 parallel units, but we need at least 2 so that we can take one offline if necessary for maintenance purposes and still have another one up in operation. Detention time should be 4 hours or more, 2 hours if lime softening is used for groundwater sources, so it can be reduced under those conditions. The water depth is typically 10 to 15 feet. However, we could have basins that are as deep as 30 to 35 feet. It really just depends on constructability and other limitations associated with the site. Dimensions, in this particular case for sedimentation basins, we want to achieve length to width ratios of 4 to 1 to 5 to 1. So meaning that the length of these basins are 4 to 5 times as long as the width. And that'll help achieve more flow conditions that are more consistent with plug flow. rather than complete mix. We also use overflow rates, which should be between 500 and 800 gallons per day per square foot. Weir loading rates shouldn't exceed 20,000 gallons per day per foot, and horizontal flow through velocities and the entrance velocity through any orifices. For example, the orifices used to disperse the flow at the inlet, that should always be below 0.5 feet per minute. And the purpose there, just like in design, like we saw with the design guidelines for flocculation basins, is that we want to make sure that the flow through velocity does not exceed this certain threshold, which could break apart the flocks into smaller pieces that might be harder to remove via settling. Are some other guidelines. The sedimentation process should follow flocculation immediately unless there's otherwise approval from the reviewing agency. The basins must be designed to minimize short circuiting. So again, we're trying to approximate those plug flow conditions and avoid the water from having a short circuit from the inlet to the outlet. One of the ways we do that is by using orifices at the inlet in order to distribute the flow evenly throughout the entire area of the inlet, as opposed to having a single pipe at the inlet that's just going to disperse the water at a single point, which would encourage it to take a short circuit route from the inlet to the outlet. So let's do an example problem. Let's assume a design flow rate of 1.5 million gallons per day. We're going to determine the dimensions for a rectangular sedimentation basin using a retention time or detention time of 4 hours, an overflow rate of 700 gallons per day per square foot, and a length to width ratio of 3 to 1. All right, so for this problem, we've got a flow rate that we're going to use for design of a sedimentation basin of 1.5 million gallons per day. We've got a retention time of 4 hours that we need to achieve. We've got an overflow rate of 700 gallons per day per square foot. And we're told to try to achieve a length to width ratio of approximately 3 to 1. So this is the starting point for our design. We're going to start using the overflow rate. So again, the overflow rate is equal to the flow rate divided by the area. And we can rearrange that equation to solve for the area. Now this area is the area looking down on the reactor, kind of like a bird's eye view. Alright, so that's the overflow rate. If we rearrange that, we get area is equal to Q divided by the overflow rate. So the flow rate is 1,500,000 gallons per day. The overflow rate we're using is 700 gallons per day per square feet. So that gives us an area of 2,143 square feet. All right, so based on our desired length to width ratio, 3 to 1, we can set this equal to length 3W times width W, or 3W squared. If we solve for the width, we get a value of W equals 27 feet approximately, which would give us a length of approximately 81 feet to use for the design. Last step is we want to look at the retention time requirements. So we have retention time equals the volume divided by the flow rate. So remember that volume is equal to length times width times depth. That's divided by the flow rate. The one dimension that we still haven't figured out yet is the depth. So if we rearrange this equation to solve for D, we get depth is equal to retention time times flow rate divided by length times width. So that's going to equal 4 hours times 1.5 million gallons per day divided by 81 feet times 27 feet. We're going to need to do a conversion of cubic feet to gallons and also days to hour. But after doing those conversions and running through the calculations, we should get a depth of approximately 15 feet. Alright, so then our final dimensions would be width equals 27 feet, length equals 81 feet, and depth equals 15 feet. That's what we can use for the design of this reactor. Alright, the next topic in this part of Module 2 is granular media filtration. So our learning objectives here are to describe the design and operation of granular media filters, to calculate filtration and backwashing rates, to design or size the dimensions of a granular media filtration system for a water treatment plant, to calculate head loss through a granular media filter. So granular media filtration is used again after flocculation, and in some cases might even be after settling. For some systems we might use what's called direct filtration, where after coagulation, flocculation, filtration goes directly. But its purpose is just like for the sedimentation or settling tank. Its purpose is to remove those particles that are flocculated, that are coagulated in the flocculation basin here, to remove those particles from the water and to discharge the clarified water. This is the most common type of filter used in water treatment plants, generally again to remove these flocks after chemical coagulation. But we do have two different types of filters that are used in water treatment. First type is slow sand filters. Second type is rapid sand filters. So we're going to be focusing most of our discussion on rapid sand filters, which are more commonly used for typical surface water treatment systems like the one you see here. All right, so first we start out with the media. So media filter has different layers of media that are specified either by the effective size of the media, by the uniformity coefficient, so how uniform is that size of the media, and also by the type of media, so what's the material of the media being used. The effective size is quantified using the D10 value, where D10 is the 10th percentile of the diameter of the particle. In other words, 10% of filter grains by weight would be smaller than this diameter. That would be the definition of D10. So that's it's what's used as the surrogate essentially for the effective size of the filter. So the 10 percentile of the particle diameter. The uniformity coefficient, which is how similar is each particle to each other, is this is quantified using a ratio of the 60th percentile diameter to the 10th percentile diameter. So again, where 60th percentile diameter is the diameter for which 60% of the filter grains by weight would be smaller. So you can see here, this would be kind of a typical curve that you would see when classifying a filter media based on its D10 and D60 over D10 values. So D10 would be where 10% or more by weight are passing this sieve size, where we might do the experiment using standard sieves like the 60 number sieve, the number 40 sieve, etc. But we would then fit a curve to those data in order to interpolate between them. You can see here that the D10 value for this particular curve is approximately equal to 0.32 millimeters. So that would be the effective size of a media with these characteristics. And again, you can see the 60th percentile is larger, 1.25 millimeters, and so therefore we could also calculate 1.25 millimeters divided by 0.32 millimeters, which would be that uniformity coefficient. Here you can see 1.25 divided by 0.32 would be equal to 3.9. So using data from a sieve test, we can determine the effective size and the uniformity coefficient of a media that's used for filtration purposes. Now, the other parameter again is that what type of media are we going to use? So we've got different types of materials that are commonly used in water treatment filters. The first, granular activated carbon, which has a specific gravity of 1.3 to 1.7, an effective size that typically ranges between 0.8 to 2 millimeters, and uniformity coefficients, which typically range from 1.3 to about 2.4. Another material commonly used is anthracite, and this has similar specific gravity, similar effective size, and roughly similar uniformity coefficient as granular activated carbon. Sand is also very commonly used in filter media, so sand having a specific gravity of 2.65, approximately an effective size of 0.4 to 0.8 millimeters, and uniformity coefficients of 1.3 to 1.7. We would also use gravel or garnet, typically going underneath the sand. So this has a higher specific gravity, a smaller effective size, and uniformity coefficient, again, of 1.3 to 1.7. Rapid sand filters operate at rates up to 100 times that of slow sand filters, using both mechanical straining and physical adsorption. So these are two different mechanisms by which dissolved, suspended, flocculated particles can be removed from rapid sand filters. So mechanical straining just means that the pore sizes between each of the grains, the sand grains or the gravel grains, these pore sizes would be too small for the larger flocks to fit through, so they would be physically or mechanically strained out. Physical adsorption means that the particles are small enough to potentially make it through the pore size. However, the surface properties of the particles are such that they are going to want to adsorb onto the filter media. So particularly with the anthracite and the granular activated carbon, there would be lots of sites where certain contaminants can adsorb onto those particles. Pressure head, which refers to the level of water and the amount of potential energy that the water has going through the filter. This is generated by a combination of water pressure from above, in other words, the initial height of the water above the filter, and also from a suction effect that happens below the filter. So creating sort of like a vacuum and pulling in pressure to help pull that water through the filter. For design considerations, again, we would use filtration rates that should range between 2 and 6 gallons per minute per square foot. And so that would be basically the flow rate that can pass through a square foot of filter media if you're looking at it from the top down. Media diameters typically would range between 0.5 and 1.2 millimeters. The bed depth, meaning the depth from the very bottom layer all the way up to the very top, is usually between 2 and 6 feet. Freeboard, which refers to the amount of space on top of the top layer that the walls are built, and that would allow the water to build up on top of the filter and apply that pressure. That's typically between 1.5 to 2 feet. The underdrain, which would go underneath the bottom gravel layer, would typically have a thickness of 1 foot or less. And the required head, which is the water pressure above the filter media, is usually between 6 and 10 feet. So there's a lot of different types of underdrain systems that we can use. For example, you can see the drawing here showing pipe laterals with orifices that can be used in some systems. This type of underdrain has a medium head loss associated with it. There's no need for air scouring, so air scouring is required in some cases for underdrains where you'd have buildup of material over time that accumulates on the surface of those drains, and that fouling, I guess, layer that we could call it, could be removed using pressurized air. So some types of underdrains would require air scouring. This particular type typically does not. However, deep gravel layer would be required on top of this underdrain. We can also use pipe laterals with nozzles. Here, the advantages here is that we can use shallower gravel levels. We would have, however, a higher head loss compared to pipe laterals with orifices, and air scouring would be required in this particular case. Vitrified tile block is another common type of underdrain system where we have a gravel layer that's relatively shallow, medium head loss through the underdrain, and no need for air scouring. And a plastic dual lateral block system where we have we can use shallow gravel layers. We can get a low head loss value through the underdrain, and however, air scouring and maybe even air water scouring would be required for this type of underdrain. Plastic nozzles can be used without a gravel layer. They have, however, high head loss, and air scour or concurrent air water scour is required. So this is kind of like a cross section of what a typical rapid sand filter might look like. You've got, again, the underdrain, in this case vitrified tile, then you've got a gravel layer, different gravel layers, different sizes, then you've got the sand layers, and up on top probably some type of granular activated carbon or anthracite. But there's different types of filters, and they're named differently based on how many layers we have. So a monomedia filter would be the type of filter that uses one layer of media, which is usually sand, and that layer is typically 24 to 30 inches deep. A deep bed filter would include one layer of media, however, would typically be anthracite or granular activated carbon. These types of filters would have to be deeper, typically 5 to 6 feet deep. Dual media filters use two different layers of media, which is usually anthracite over a layer of sand. They have dimensions that are typically 18 to 24 inches for anthracite, 9 to 12 inches for sand. These filters are more robust than the monomedia or deep bed filters. And then mixed media filters utilize typically 3 layers of media, anthracite over sand over garnet, and the ranges of the media diameters would typically used with this type of filter are shown below. 18 to 24 inches of anthracite, 9 to 12 inches of sand, 4 to 6 inches of garnet. These are the most robust rapid sand filters. So again, this is a conventional filtration system using raw surface water, might have sedimentation followed by filtration. This process, if used in this configuration with coagulation, flocculation, then sedimentation, and then filtration, we'd be able to use this type of configuration for any surface water that has turbidity values of 20 NTU all the way up to 1000 NTU. For cleaner surface waters or for groundwaters that have turbidity of less than 15 NTU, and where this turbidity value has low variability, we can use what's known as direct filtration. So you see the difference here is that we just kind of skip the sedimentation step, going straight to filtration after flocculation. So this saves us a lot of space in the treatment system, saves us a cost associated with sedimentation, but it can only really be used for waters with low turbidity. Other types of filtration schematics include inline filtration or contact filtration. We might have pretreatment using coagulation and flocculation as described earlier, but this inline filter or contact filter would normally only be used with water sources that are very pristine, having low turbidity below 10. Two-stage filtration includes pretreatment, coagulation, followed by two separate stages of filtration. The first stage is including coarse media, and this is appropriate for surface waters with turbidity of less than 100 NTUs. It's often also available as pre-engineered systems for smaller installations, kind of like package plants you might see in smaller towns and communities. So how do we operate a rapid sand filter? Let's suppose we have a filter setup shown here. So we've got The inlet water coming in through this pipe right here is shown pipe number 1, settled water from coagulation, and it comes in up through this channel into the area where the filter media is located, and then flows downward through the media and out through the underdrain, where we can divert it into different directions based on these 4 valves here, or 5 if you count the backwash water. So the valve's closed, of course the water won't pass by. If the valve is open, the water can pass through. So we would typically operate rapid sand filters the following way. First, we would have only valves 1 and 4 open, so this would allow the water to come in, move through the filter, to leave through the bottom, and then exit into the filtered water into what we call the clear well, where we would then seek to achieve chlorination and fluoridation. So valves 2, 3, and 5 would all be closed under this scenario. All right, so this is normal operation of the filter. After a while, we would want to take a filter offline in order to perform backwashing. So the first step would be to close valves 1 and 4, to close valve 3, and to open valve 2, allowing the water to drain off over the top and exit the system by going through valve 2, which collects wash water that would be sent to disposal or back up to the headworks of the treatment plant. After this step, we would typically sparge the media with air to try to dislodge some of the accumulated material that is built up over time. And then we would perform backwashing. So the air sparging would dislodge some of that material, and then the backwash water would be provided to the filter by opening up valve 5. We would close valves 1, 3, and 4, and we would keep valve 2 open. So this backwash water would come, which is usually treated water, would come down through this pipe and go up through the filter media, lifting up all of the settled particles and the accumulated solids, lifting it up with the backwashing water, where it would spill over to the side and then exit into the wash water pipe, where it would be disposed of or treated again. After backwashing is complete, we would then open up valve 1 again, allow the raw water to, or coagulated raw water to come up through the filter, pass through the filter again. However, at the initial stages of, in the initial moments after backwashing a filter, the first kind of flush through the filter would be wasted. So in order to wait until the turbidity levels come down to normal levels again, in which case we would close valve 3 and open up valve 4, letting that filtered water go again into the clear well for disinfection and distribution. All right, so the filter bed is placed inside a concrete box. Typically, the water passes through the filter by gravity, also based on suction from the bottom of the filter. As you can see in the previous slide, the clear water depth of the clear water level would be below the bottom of the filter media. This creates that suction effect, increasing the pressure head above the filter. The water depth above the filter surface is typically between 3 and 4 feet. And then the filter is backwashed when the head loss through the media gets to be too high. So under average operating conditions, this is usually taken place, programmed every 24 hours. The backwash rate used is usually about 15 gallons per minute per square foot, and the duration would be between 10 and 15 minutes. The initial 3 to 5 minutes after backwashing, after flushing out all of those solids, that initial 3 to 5 minutes would be wasted. The water would be wasted. And then we would go to distribute that water into the clear well after the turbidity levels stabilize. 2 to 4% of the filter water would be usually used in backwashing. So in order to budget for how much water can be produced, there is some loss, of course, because some of the water that's passing through the filter will have to be stored and then will have to be used for backwashing processes, and that percentage is usually 2 to 4%. So another important aspect about filter design is to calculate the head loss during filtration. So head loss can be calculated using the following formula, which has two different components. We've got head loss due to viscous forces, and we've got head loss due to inertial forces. And the two components added together comprise the total head loss. So here you can see all the different parameters that are part of this equation. So we have things like the absolute dynamic viscosity of water, we've got the density of water, the depth of the granular media, the effective diameter of the media, porosity, the acceleration due to gravity, and velocity or filtration rate, V, here. And depending on the medium, we have these coefficients, K sub V and K sub I, as well as the porosity value, which would typically range between these levels for sand or for anthracite, depending on the medium that we're using in the filter. And so this equation is for a clean bed filter. However, it should be noted that head loss increases as more and more particles are retained on the filter. When it increases to a level that's too high, of course, we would need to initiate backwashing. So this setup right here shows a second type of filter, which is a slow sand filter. So the previous slides were depicting rapid sand filters, which are most commonly used in water treatment systems for surface water. However, slow sand filters are also used in some settings, and the difference here really is that we have a larger head above the filter starting point, and so we've got more water up on top of this filter, the top of the filter, and the media would typically be finer grain. The flow rate through the filter would be slower, and we would mostly be relying on biological growth within the filter media. So that biological layer that develops on top of the filter media would be responsible for much of the treatment that occurs in the slow sand filter. We're not going to cover the details of designing slow sand filters in this class. We'll be focusing on rapid sand filters. So again, head loss during the filtration process will increase at a rate that is usually typically linear. And so you can see here at time 0, we have a low head loss. And as we accumulate material on the filter, that head loss is going to increase. And eventually we will get to a point where we need to backwash. And after backwashing, we would bring the filter back into operation again. And as you recall in the previous slide, I said the first few minutes of running the filter after backwashing takes place, that water would be wasted. It wouldn't be sent to distribution. The purpose of doing that is because while the filter's kind of getting acclimated again, the turbidity levels will spike during this first phase. This is what we would call the ripening phase. And then we would have a period of time where we have pretty effective filtration. Eventually, we're going to get to the point again where the filter clogs up to a point where we would experience what's known as breakthrough. That's when all of a sudden there would be a spike and increase in the turbidity levels of the water in the effluent of the filter. And before we get to that point, we would really want to initiate backwashing. All right, so at the beginning, turbidity is high as the filter goes through the ripening stage. Then we get to an effective filtration stage where turbidity is low. Turbidity will then increase again after a breakthrough time, which is usually more than 24 hours. Let's do an example problem. Suppose we have a rapid sand filter that's 15 feet by 30 feet in dimensions. And after filtering 2.5 million gallons over a period of 24 hours, the filter is backwashed at 15 gallons per minute per square foot for a time of 12 minutes. So for this example problem, I want you to compute the average filtration rate in gallons per minute per square foot, and then figure out how much wash water is needed in gallons and what percentage of treated water would be required for backwashing. Alright, so for this problem we've got a filter which has dimensions of 15 feet by 30 feet, and we're told after filtering 2.5 million gallons in a 24-hour period, the filter is then backwashed, and the backwashing occurs at 15 gallons per minute per square foot for a duration of 12 minutes. And we're asked to compute the average filtration rate, then to find the quantity of wash water needed and the percentage of treated water used for backwashing. So to calculate the filtration rate, we want to look at the volume or the flow rate of water treated, which is 2.5 million gallons per day, and we're going to divide that by the dimensions of the filter, 15 feet by 30 feet. To express this as a flow rate per unit area of the filter. So that would be the filtration rate. Alright, so we'll need to convert gallons to, well, we can keep it actually in the units, gallons per minute per feet squared, just like the backwashing rate. But we will want to convert days to minutes, so we'll add down here 1440 minutes per day in the denominator. And if we do that calculation, we get a filtration rate of 3.9 gallons per minute per square foot. So next step is to calculate the volume of wash water needed and to compare that to the amount of water that we're treating during a 24-hour period before backwashing, so that we can get an idea of the efficiency of the filter, the rejection rate. So to calculate the volume of wash water needed, we're going to take the 15 gallons per minute per square foot, multiply that by the duration, 12 minutes, and then multiply that by 15 feet and by 30 feet to cancel out the square feet. That'll give us a volume of gallons, which should be equivalent to 81,000. Alright, so in a 24-hour period, we're treating 2.5 million gallons, and then we're backwashing with 81,000 of those gallons. So the ratio of wash water to treated water is 81,000 divided by 2.5 million. And that gives a rate of about 3.2%. So basically 3.2% of the water that we treat needs to get used for backwashing, so it won't be available for production. Therefore, the efficiency of this filter would be 96.8%. All right, let's do another example. Suppose we have rapid sand filters for a water treatment plant that are treating a flow of 60 million gallons per day. The filtration system is preceded by coagulation, flocculation, sedimentation. Let's use, for this case, we're going to design the sand filters, meaning, choose a size, choose dimensions for them, choose the media, determine the thickness of each media layer, determine the underdrain, etc. So let's use, for this flow rate, let's use 1.5 for a peak factor, and we'll choose an appropriate number of parallel trains based on our backwashing schedule and how many filters we need to have online at a time. Then determine the surface area for each filter, select a media type, determine the depth of each filter, and then determine the dimensions for each filter, and we'll draw a sketch showing the media, the gravel, the underdrain, the overflow troughs, and the freeboard. We'll label the dimensions and show the total required pressure head and the water level in the chlorine contact basin. Alright, so this is a design problem, and we've got a flow rate of 60 million gallons per day with a peaking factor of 1.5. So that means that the peak flow will be 90 million gallons per day. Alright, so the first part of this is we determine how many filters should we have in parallel. This is really kind of a discretion of the engineer type decision in terms of what makes sense. You got to keep in mind that you're mostly always going to have at least one filter offline for backwashing or for maintenance, and so you want to be able to handle the peak flow when you have all your filters up and running, but during normal flow conditions you want to be able to have one of them offline if you need to do some maintenance. And so peaking factor of 1.5, we can kind of divide that by 3 so that you can imagine if we have a flow rate of 90 million gallons per day, we've got all 3 filters running in parallel. When we're at average flow conditions, 60 million gallons per day, we've got 2 filters up and running. If we have lower flow conditions, like down to 30 million gallons per day, maybe we only have 1 filter up and running. So at the minimum, I would say 3. However, for a more robust system, you might want to double that to have 6. That gives you flexibility to use 5 at a time in case one of them needs to be offline. So let's just suppose we have 6 in parallel. Alright, so our flow rate is getting split into 6 equal parts. And we want to calculate next the filtration rate, or sorry, the surface area based on a filtration rate. So we want to know what is the surface area of each of these 6 parallel filters. Alright, so according to the design standards, filtration rates should be between 2 and 6 gallons per minute per square feet. So let's use 4 for the purpose of the design. Alright, so we can calculate the surface area using our flow rate, our peak flow rate for design, 90 million gallons per day, divided by 6 filters in parallel. Remember that flow is being split up into 6 equal pieces. Then we're going to divide that by 4 gallons per minute per square foot. We'll need to convert this days to minutes using 1 day is equal to 1440 minutes. And then solve for the surface area. That should give us a value of 2,604 square feet. So that would be the required surface area of each of these 6 parallel filters. Next part C, is to choose a media type. So we solved we went through part A. Part B is here to find the surface area. Part C is to determine the media type and the depth of each of the filters. Alright, so here's again at the discretion of the engineer. Let's use mixed media filters. These filters are robust. They have 3 different layers of media: anthracite over sand over garnet, with typical depths of certain ranges of depths that are specified in the design recommendations. So let's use mixed media filters. So for anthracite being the first layer, the second layer being sand, and then garnet. So, and then remember, under the garnet we always need to have our gravel layer and underdrain, which have a depth as well. So if we look at the design guidelines, typical depths of anthracite would be 18 to 24 inches. So let's use 1.5 feet for that layer. For the sand layer, typical depths are 9 to 12 inches. So let's use 1 foot. For the garnet layer, 4 to 6 inches is typical, so we'll use 6 inches. And then the gravel layer should be 8 to 16 inches. So we're going to let's use 1 foot. Alright, so that's a total media depth right here of 4 feet. Right now, don't forget that we need some extra distance above the media for freeboard. Right, so we've got 1.5 to 2 feet of freeboard. Let's use 2 feet. And we've also got the distance from the top of the media to the bottom of the trough. So our troughs are up here, right, delivering the water and collecting backwash. We have a distance from the bottom of the trough to the top of the media. That should be, again, maximum of 30 inches. Let's use 2 feet. The freeboard should be 1.5 feet to 2 feet, so we'll use 2 feet. So this is 2 feet. This is 2 feet. Alright, so underneath the gravel again, we've got our underdrain. Depending on which design we use for the underdrain, it could be up to 1 foot. So let's say that's another foot. So we've got 1 plus 4, that's 5, plus 4, that's 9 feet. That's a total depth of 9 feet for the filter structure. Now, for part D then, we are to determine the dimensions of the filter and draw a sketch of it, showing the media, the gravel, the underdrain, the troughs, the freeboard, etc. And we want to make sure that we've got the right amount of pressure head for this filter, given what we've got with water level above the filter and the suction from below, the distance between the bottom of the filter and the water level in the chlorine contact basin. So here, again, we've got a surface area that was determined in the previous step. Surface area is 2604 square feet. We'll have to choose a length to width ratio. We've already got our depth is set based on our media and the freeboard requirements, etc. Length to width ratio could be up to us as engineers to determine what makes the most sense in terms of constructability and what fits into our site. Let's use a 2-to-1 ratio. So let's use a 2-to-1 length to width ratio. That means that 2604 is equal to 2W times W, and we can solve for W, which would be equal to 36 feet, making the length equal to 72 feet. And again, our depth would be a total of 9 feet for the structure. So here we can see a sketch of the designed filter with a 1 foot underdrain, a 1 foot gravel layer, a 6-inch garnet layer, a 1 foot sand layer, a 1.5 foot anthracite layer, clearance of 2 feet between the top of the anthracite and the water troughs, a freeboard of 2 feet. Again, our width is 36 feet, our depth is 9 feet, and our length is 72 feet for the structure. This allows us to have a total pressure head of 10 feet. One more example, let's calculate the clean bed head loss through a deep bed dual media filter with 1.5 meters of anthracite with a size of 1.1 millimeters, and that layer is over a 0.3 meter layer of sand with an effective size of 0.5 millimeters. Suppose that the filtration rate is 15 meters per hour and that we have a temperature of 15 degrees Celsius. Alright, so for this example problem, simple implementation of that head loss equation, and we're going to do the calculation separately for each layer. So we've got the anthracite layer, we've got the sand layer, and then we're going to add up those two head loss values to get the total head loss over the filter. I'll do a demonstration for the anthracite layer. Alright, so we need to choose a value for K sub V, K sub I, and porosity. We've got the range of typical values from that lookup table. So let's use a K sub V value of 228, just kind of right in the middle of the range provided. K sub I, let's use 4.4. And for porosity, let's use 0.5. And in a problem like this, design problem like this, we just want to be explicit about our assumptions, make sure they're realistic. For the rho value of water, for the density of water, we're going to look that up using a table based on the temperature of the water. Alright, so for the temperature that we're working at, we've got a density value of approximately 999 kilograms per cubic meter, and mu, dynamic viscosity, at that temperature is equal to 0.00114 kilograms per meter per second. Alright, so next we're going to implement the equation for head loss, and remember that's got two components. It's got the inertial head loss, and that's the first component, and then it's got the viscous head loss due to viscous forces is the first component. The head loss due to the inertial forces is the second component. Alright, so implementing that equation with the assumptions we're using, we've got head loss is equal to 228 times 1 minus 0.50, that's going to be squared, times 0.00114 kilograms per meter per second, times 1.5 meters, that's the depth, the rate 15 meters per hour. So that's the numerator. The denominator of this portion of the equation is 0.50 cubed times the density, 999 kilograms per cubic meter, times G, 9.81 meters per second squared, times our diameter, 1.1 millimeters. That's going to be squared. We need to convert millimeters to meters, so 0.001, and that's meters per millimeter. That also needs to be squared, and then we need a conversion from seconds to hours, so that's 3,600 seconds to hours. Alright, so that's the first term in the equation, the viscous forces. The second term then, due to the inertial forces, is equal to 4.4 multiplied by 1 minus 0.50 multiplied by 1.5 meters, then 15 meters per hour. That's going to be squared. That whole thing is divided by 0.50 cubed times 9.81 meters per second squared, 1.1 millimeters squared, and then the unit conversions. Alright, so we've got 0.001 meters per millimeter squared and 3,600 seconds per hour squared. Alright, so you implement that equation, that should be equal to 0.31 meters. Now, as with any equation that's kind of this involved, you want to double check, triple check the units, make sure everything is making sense, make sure the units are canceling out and that we're left with meters. And we just want to do a check too to make sure, does this value make sense? 0.31 meters, is that within a reasonable range? Alright, for the sand layer, it's going to be an identical implementation of this calculation. I'm not going to draw that entire equation out, but you can say that that should be equal to a value of 0.33 meters. Therefore, the total head loss for this filter would be 0.31 plus 0.33, or 0.64 meters.